All right. So we now are going to wrap up the conversion topic to talk about, just in general, how do you convert from one space to another using the Jacobian? First, the Jacobian is some kind of scaling parameter so that we can go from one space to another. So one space to another. And we saw previously how we can use it to convert from rectangular, xy, to polar from with r, and in reference to here, theta. Or how we could use it to convert from a 3D rectangle, or a rectangular prism, z, x, y, to cylindrical with radius r, angle theta, height z. And lastly, with 3D Cartesian, we showed how it was also useful for converting from 3D Cartesian to spherical. So we have rho, the angle over here is theta, and just in general, the angles over here is, or not theta, phi, and the angle as it goes across is theta. Now, what happens when we just have any kind of space converted to any other kind of space? So suppose it was contained with u1, u2, u3 as our parameters. And then we have maybe v1, v2, v3. Well, at least for this specific situation, the Jacobian doesn't change. We know how u1 is related to v1, u2 is related to v2, and u3 is related to v3, and these are k1, 2, and 3, which are our relation parameters. We could find a Jacobian for it. And this Jacobian will give us something in which it will relate one triple integral of the u parameters to another triple integral of the same parameters but in relation to v, scaled by a Jacobian. Just in general, we can expand this to any kind of space, small or large, and we can show that regardless, we're able to find a relation between the two using this Jacobian matrix, which is our scaling parameter in order to go from one to the other, from one space to the other. Here, the Jacobian was rho squared sine of phi. The relation here was r. And finally, the relation here was also r. So the Jacobian is a very powerful tool which we can use to turn one space to another through some kind of scaling. So lastly, just in general, the entire formula, if we're expressing it in general, x11 divided by xt11, x12, xt12, x13, t13, so on and so forth. And in this direction, x21, xt21, xt31, 2, 3, 1, and it expands forever in this dimension. And it'll also keep expanding over here in this direction. And we can keep going on. And this allows us to generalize any kind of space. But the caveat is this is not useful. Not useful in the sense that we don't generally deal with parameters that are greater than 2 or greater than 3. So at most, because at most we have 3 independent variables. So the discussion about finding the Jacobian in 4-dimensional space, 5-dimensional space, 10-dimensional space becomes impractical because we can't exactly use it to our advantage. So we have 3 independent variables at most. And the most useful transformations would be from Cartesian to cylindrical to spherical. Or if we're talking about 2D, from Cartesian to polar. And these are the ones which dominates the majority of our discussion because we can see practical uses for converting from one to another mathematically. However, looking at this space, if we were to express a general way to find the Jacobian, this would be how we would do it. However, as mentioned before, this isn't useful because of the fact that our minds cannot really practically understand 4D, 5D, 10D spaces. This becomes more of an abstract mathematical object. The most useful and the best case scenario only is 3 independent variables, and these are useful for symmetry. There are other spaces. There are elliptical coordinates. There are hyperbolic coordinates. However, in the scope of electrical engineering and in most undergrad courses, the most useful to know would be these 2 conversions, either in 3D or in 2D. And that wraps up about our conversation and our discussion about conversion from one to the other, and just in general about multivariable calculus, multivariable integration. I hope you found this insightful. In the next video, we're going to work on some example problems. Thank you.